Hello, I'm Mark Dickinson from NSF's Noir Lab in Tucson, Arizona, and I'm here to speak about the Atlas probe, a space observatory to study galaxy evolution and cosmology from spectroscopy of 200 million galaxies out to redshifts of 7. Now, galaxies form and evolve in the context of large-scale structure, the so-called cosmic web of dark matter and baryons. And understanding this requires both mapping large-scale structure with some precision and measuring galaxy properties as both evolve over cosmic time. That means galaxy redshifts and velocities, and the properties of the interstellar medium and the stellar populations of galaxies. Now, in the local universe, surveys like the Sloan Digital Sky Survey or GAMMA, using wide area high multiplex spectroscopy, have accomplished this with outstanding statistics and high quality spectra. And now this is being pushed to higher redshifts with larger telescopes and high multiplex spectroscopic instruments, measuring galaxy clustering at higher redshifts, but with limited spectral coverage and signal to noise ratio. For a long time, we've been taking deep spectra in small areas of the sky to measure galaxy redshifts out to the epoch of reionization, but with limited volume, statistics, and spectral coverage. We're all looking forward to the James Webb Space Telescope, whose near-spec multi-object spectrograph will observe at 1 to 5 microns to measure optical rest frame spectral features out to very high redshifts, but again with small volumes and numbers. Atlas probe is the Astrophysics telescope for large area spectroscopy. It's a space mission concept for a probe class mission from NASA, 1.5 meter aperture telescope with a 0.4 square degree field of view, carrying out resolution 1000 slit spectroscopy at 1 to 4 microns of up to 6,000 objects simultaneously. This could be ready for launch by 2030. Its science objectives are to map the cosmic web to shed light on the physics of galaxy evolution, to trace large-scale structure densely to illuminate the nature of dark energy, and although I won't be talking about it here, to probe the Milky Way's dust enshrouded regions and to explore small bodies in our outer solar system. The principal investigator of Atlas probe is Yun Wang at IPAC at Caltech. Our primary partner for this mission would be the Jet Propulsion Laboratory, and the instrument lead is Massimo Roberto. And you can read much more about Atlas probe in much more detail in the paper Wang et al. 2019 that is indicated toward the bottom of the screen, and you can check our website for more details. The key enabling technology is digital micromirror devices. These are commercial off-the-shelf devices built for digital projectors and projection TVs. They are arrays of large numbers of little mirrors that tip back and forth. In Atlas probe, a mirror would act as a slit selector. It would direct light from an object to the spectrograph in one position, or away from the spectrograph to a light dump in the other position. These were studied for JWST, but not used. They were studied for a Euclid precursor concept called space. And Atlas would use the latest generation of Texas Instruments DMDs, which are 2048 by 1080 elements on a side, more than 2 million micromirrors, providing a very great capacity for multi-object slit spectroscopy. The preliminary optical design is shown here at left. This would have a single instrument with 4 identical modules. Each module would have 2 spectrographs, the light split by a dichroic, 1 to 2 microns in one channel, 2 to 4 microns in the other. And each digital micromirror DMD mirror projects to a 4K by 4K infrared detector with a pixel scale of 0.39 arc seconds per pixel. The DMD micromirrors would be 0.75 arc second on a side apertures for selecting objects for spectroscopy. Spectral resolution of about 1,000, multiplex up to 6,000 objects, and a total field of view of about 0.4 square degrees, which is comparable and larger, in fact, than that of the Roman Space Telescope Wide Field Imager. And in fact, the Atlas probe is conceived as the spectroscopic follow-on mission to the Roman Space Telescope. Now, for studying galaxy evolution, spectroscopic redshifts of galaxies over large areas and high number densities are needed in order to connect the properties of galaxies, such as stellar masses and star formation rates, to the underlying dark matter halo masses and the environments of galaxies. We envision a notional three-tier survey with Atlas, a wide survey covering the Roman high latitude survey 2,000 square degree area and 183 million galaxy redshifts out to redshifts of order 5. There would be medium and deep surveys covering smaller areas to greater depth, but still surveying millions of galaxies out to very high redshifts. The rest frame optical spectroscopy enabled by observing at 1 to 4 microns is very much like we've all been thinking about for the James Webb Space Telescope and NIRSpec. At right, you see simulations of how a star-forming galaxy would be at a redshift of 3 observed with Atlas, how it would detect lines like H alpha and nitrogen 2 out to redshifts of 5, oxygen 3 and H beta out to redshifts of 7. Allowing diagnostic measures of the interstellar medium conditions, chemical abundance, physical conditions in galaxies that are not possible with less detailed spectral information. At left, you see the capabilities of the Atlas Deep Survey for studying the stellar continuum and absorption line spectroscopy of quiescent galaxies, galaxies that are not forming stars. This is essential for understanding their ages and star formation histories. Atlas would densely sample cosmic structure in order to understand how the evolution of galaxies depends on their environment. In the images you see here, the green is a dark matter simulation of large-scale structure at redshifts of 2, and the red dots are individual galaxies whose redshifts would be measured spectroscopically. At left, the galaxies measured by the Roman Space Telescope Slit Spectroscopy, and at right, the much denser sampling that could be achieved with Atlas Slit Spectroscopy. And slit spectroscopy has a number of important advantages. It greatly reduces the background compared to slitless spectroscopy and increases the signal to noise ratio. And that enables high spectral resolution to trace the cosmic web with great fidelity, much greater than can be done with photometric redshifts as shown at the right. And that would be very good photometric redshifts indeed to see large scale structure at that kind of resolution. Or slitless spectroscopy from Euclid or Roman. Atlas would provide a much higher, sharper definition view of large-scale structure at high redshifts. And this, for very large samples of galaxies, tens or hundreds of millions of galaxies, would let us divide galaxies in bins by redshift, stellar mass, star formation rate, morphology, etc. And in those bins to measure the clustering of galaxies, which in turn constrains the dark matter halo masses. And this enables science that we simply can't do right now. For example, directly measuring the stellar mass halo mass relation as a function of galaxy properties and redshifts, or to derive individual halo masses from group catalogs by identifying central and satellite galaxies spectroscopically, measuring environmental densities out to redshifts of 3, or average dark matter accretion rates by the detection of the so-called splashback radius or turnaround radius of satellites. Spectroscopically identifying galaxy pairs to measure the evolution of merger fractions and merger rates with cosmic time. There are many other applications. We'll be able to get dynamical mass constraints on galaxies from emission or absorption line widths spectroscopically, and the galaxy sizes and morphologies from Roman imaging. We'll be able to identify active galactic nuclei over a wide range of luminosity and redshift, and to study them in the context of local and large-scale environment. Identify bound galaxy clusters and groups at cosmic noon, and to study the galaxy properties and cluster and group dynamics. Identify pre-virialized protoclusters out to redshifts of 7, and at redshifts beyond 7, study Lyman alpha emission from Roman color-selected galaxies. And ultimately, when the square kilometer array and other experiments measure neutral hydrogen with 21 centimeters, we'll be able to correlate that at the epoch of reionization with the large-scale distribution of galaxies observed by Roman and Atlas. Atlas is also a powerful tool for cosmology. It will definitively measure the cosmic expansion history and the growth history of large-scale structure through redshift space distortions, particularly at redshifts greater than 2, with much greater accuracy than any other ground or space-based mission is capable of doing. It will enhance the Roman Space Telescope weak lensing measurements by providing spectroscopic redshifts for 70% of the Roman high latitude survey weak lensing sample, down to H magnitude of 24.7. So in summary, Atlas probe addresses fundamental questions in astrophysics, both for galaxy evolution and cosmology. And although, as I say, I didn't talk about it, our own galactic structure and the outer bodies in our solar system. The mission implementation is expected to be straightforward. There are no significant technical risks, and this could be launch ready by 2030. The cost and schedule estimates are compliant with a NASA probe class mission, and we're ready to develop and submit a proposal if NASA issues an AO for probe class missions. The community support for Atlas is strong. We have an open collaboration, and we're always looking for new participants, so please contact us if you're interested. And coming soon, there's an opportunity to learn more at a community workshop that we'll be holding on the 21st to 23rd of June. The Massively Parallel Large Area Spectroscopy from Space Atlas Probe Community Workshop. This is going to be held during Euro-friendly hours of the day online. The registration will be open soon at the website you see here. So I hope you'll be able to join us for that meeting. There'll be some excellent presentations and opportunities for you to learn more about Atlas. Thank you very much.